today, as we finish off section 3, I want to make a connection here, an application really, to using our synthetic division, okay? We have the same process that we use for synthetic division, and what we can do is use what's called the remainder theorem. The remainder theorem. And what it says is this: if we divide some polynomial f of x by x minus k, the remainder is r equals f of k. Alright? Now, there's some notation there, but I think we can interpret this. Can someone put that theorem in their own words? What would this theorem allow us to do?
You could plug in the k and find the remainder.
Okay, if you plug in k into your function, that will give you what your remainder is going to be, right? Now, we can use this theorem that way. However, the more common use for this would also be if you do the synthetic division, whatever you get for that remainder is the function evaluated for k. Okay? So, it has a dual purpose. You could check to make sure you got the right remainder by evaluating the function at k, or you could figure out what f of k should equal by doing the synthetic division and getting that remainder. Okay? Now, guys, that's why when you get 0 at the end, what do we know about k? X minus k is a factor of the polynomial, and k itself would be a 0. Alright, because it made the entire thing equal 0, and we know that because the remainder is 0. Alright, we mentioned this a little bit in the previous section where with zeros specifically, but synthetic division can be used to evaluate an expression. Alright, the remainder will equal the value. So, and this will give us a good kind of warm up and reminder of how to do this synthetic division. Okay, let's evaluate this function f of 4. Okay, one thing that I like about this, doing it this way, you might say, well, why don't I just plug in 4 and get the number? Well, the one thing that is nice about this method is it keeps our numbers a little bit smaller, okay? I don't have to find what 4 to the third power is. It's not that that's huge, I mean it's 64, but with other numbers, you know, it could get really big if you're just plugging it in, but here we can actually do the whole thing in our head just using this process of synthetic division, okay? So, if you recall, what we do for the synthetic division is, first of all, list the coefficients, smallest to largest, so 5, -7, 3, and -10. Okay? We're going to evaluate at 4. Okay? And then what's the, what did we say our mantra was? We're going to
go down.
Go down and across.
What do we do when we go down?
Add.
We add down and we multiply across. Add down, multiply over. Okay, so 5 plus 0 is 5, and then we multiply by 4. Okay, so there's 20. Multiply over. -7 plus 20 is 13, times 4 would be 52. Add down, 55. Multiply over, we get 220. Then we add down and we get 210. Alright? So here's a question. Is x minus 4 a factor of the original function?
No.
No, because we didn't get 0 at the end, right? But what does f of 4 equal?
210.
That's right. F of 4 equals 210. Okay. Because that's the remainder. So you see here, guys, this process tells us two things. As we saw on Friday, this process tells us that our function will equal x minus 4 times, it was x cubed, so that's a 5x squared plus 13x
Plus 55.
plus 55.
Plus 210 over x minus 4.
X minus 4.
Yeah. Alright, so this process tells us this is true, as we saw on Friday, but now we also see that this same process gives us the value of the function at 4. Okay? So, a nice process to use to give us really two useful pieces of information. Okay? Any questions about this? Alright, good. So that's our remainder theorem. The remainder theorem. Now, probably the question that has come into your mind as we've done this, and we've kind of mentioned already, is, well, if I were trying to factor this, how would I know to try to divide by, say, an x minus 4? Or how, where are they getting these factors from? Well, we have a theorem, and this is where we're going to spend the majority of our time today. Yeah.
We did the 55.
Oh, here we just added down 3 plus 52. You add straight down. 5 plus 0 is 5. Notice each of these we're adding straight down. But to get this number, we multiply 5 times 4. Then we add down to get 13, multiply by 4. And the same thing, add down, multiply by 4, and add down. Okay? Alright, so where, how are we going to come up with these? Do we just pick random numbers? Obviously not, okay? This brings us to our, and if you noticed, our essential question was, how do we factor things we can't factor? Okay? How do we factor stuff that we can't factor? We don't see a pattern there. We can't really do grouping even. How do we factor stuff that we can't factor?
I wonder.
Okay? Well, what we're going to do is repeated division. Okay? You can see here we have a quartic function, x is to the 4th. And in this case, we're again told 2 of the factors. Let's say logically we were just able to figure out what 2 of the zeros were, so we're able to do that. Okay? I can figure out the rest of the factors by first of all dividing. If I divide by the x minus 2, and then divide by the x plus 3, what polynomial, what degree polynomial will I end up with?
X squared.
Yeah, I'll end up with a quadratic. And guys, you guys know how to factor quadratics. Alright? So the idea here is to use this process to get down to something we know how to factor. Okay? So let's again work through the process to divide by the x minus 2 first. Okay? So we list out the coefficients, 2, 7, negative 4, negative 27, and negative 18. By the way, since we know this is a factor, what should our last number be?
0.
This should end up being a 0. I'll put it like dotted, so we know that's what we should end up with. What's the k value that we're using?
2.
2, alright? And positive 2, notice. Alright? So we run through the process again. Add down, multiply by 2. Add down and get 11, multiply by 2. Add down to get 18, multiply by 2. Add down to get 9, multiply by 2, and negative 18 plus 18 is 0. Okay? So notice here, now we have the function written as x minus 2 times 2x cubed plus 11x squared plus 18x plus 9. Right?
Why don't we just plug 2 in the functions?
What?
Why don't we just plug 2 in the functions?
Well, notice what we're trying to do here. We're trying to factor. So we're trying to write this out into separate factors. If we just plug 2 in, all that would tell us is the remainder. Okay?
I have a question.
We actually want the whole polynomials. Yes?
I don't know why if it is 2, the reminders must be 0.
If this is 2, why this has to be 0?
Yeah.
Because they told us that these are factors. Anytime it's a factor, it's going to have a remainder of 0 because it's going to factor out evenly. Okay? There won't be a remainder left if it actually is a factor. Okay? Back here on the first one that we did, this would not be, we can write it this way, but we would not say that x minus 4 is a factor of this polynomial because we had a remainder. It didn't come out evenly. Does that make sense? Okay. Alright, so to continue this, we need to divide by x plus 3 now. What are we going to divide by x plus 3?
Minus x cubed
The new one with the x cubed.
divided by minus 3.
We're going to divide it and we're going to use the minus 3 this time. You're right. Okay? So k is going to be negative 3. We're going to list the coefficients 2, 11, 18, and 9. Okay? So then we do our process. 2 times the negative 3 this time is a negative 6. Add down and get 5. Times negative 3 is negative 15. 3 minus 9, and good thing it came out to 0 like we expected it to.
Why'd you do the 2 first rather than the negative 3?
Just because we felt like it.
If you would have done the negative 3, would it have still worked out?
It would still work out. Now, if you did the negative 3 first, this would have obviously been different. You wouldn't have gotten 2, 11, 18, and 9. You would have gotten something different. But when you got down to this point, once you do the second step, you would have gotten the same thing here. Because now we know that our original function could be written as x minus 2 times an x plus 3 times,
2x squared plus 5x plus 3.
there we go, okay? Now we have something we know how to factor. This is a quadratic function. Alright, you guys know how to use the Bob method or whatever method that you guys called it.
What?
Some
The
people
FOIL?
do that. Well, you're undoing FOIL. You're factoring a trinomial. Whatever method you call it, I always called it trial and error because you're just kind of trying stuff till you find something that works.
Bob error. Which one?
The Bob method, that's what people last year said they used, but I don't know. I had never heard of it before. It kind of works, but I like just doing this, okay? I got my 2 sets of parentheses, 2x squared, the only way to factor that is with a 2x and an x. The only way to get a positive 3 is if these two signs are the same. And the only way to get a positive 3 and a positive in the middle is if both of these are positive. So now I just need factors of 3
1.
and arrange them in a way so that I'll get 5. So I'm going to put the 3 here and the 1 here, so it'll be 2 times 1 is 2, 3 times 1 is 3, 2 and 3 gives us 5 in the middle like we're supposed to have. So, I now know that my whole function f of x equals that in its fully factored form.
That's the answer.
Okay? That is what we're looking for. Find the remaining factors of f of x. So we found our last two factors of f of x. And then we could then say, alright, well then that means our zeros would be
2
x equals 2,
minus 3
good,
Negative 3 out.
minus 3 over 2
good, and
minus 1.
good, and minus 1. Okay? So you can kind of see where this process is taking us, obviously towards graphing, and also solving problems. You know, if this were a function modeling something, now we know where all the zeros of that are. And we also knew that the y-intercept was negative 18 to begin with, so we could get a pretty good graph, pretty good sketch of the graph here, just from the information we now know. Okay? Alright, so, again, we're asking ourselves, okay, well that's nice, but where are they getting x minus 2 and x plus 3 from? Okay? We have what's known as the rational zero test, or... Whoa. There we go. I don't know what's going on with that. Let's try that again. The rational zero test. You might also hear me call this the rational root theorem out of habit. It's rational roots is what we're dealing with. Okay? If the polynomial, here's just some random polynomial, has integer coefficients. Notice that, that's one important thing, integer coefficients. So we're not talking about ones that have like 4/5 x to the 5th or something like that. It's got to have all integers. Every rational zero of f has the form p over q, where p and q have no common factors other than 1. P is a factor of the constant term, so, and q is a factor of the leading coefficient. Alright, this is our rational zero test, or rational root theorem. So, to kind of summarize this, your possible rational zeros are going to be made up with a fraction, using factors of the constant term over factors of the leading coefficient. Okay? Now, let's take a look at this. Okay? Here we have a cubic equation, or cubic function, and if you look at it carefully, you can see that there actually is not a way to factor this by grouping. Okay? So there's no way that we can use one of the patterns that we've already come up with, or we've already learned in order to factor this. So, let's think about this. Our constant term is what in this case?
3, I guess.
Yeah, it's 3. Okay, right here. What are the factors of 3?
Plus or minus 1 and plus or minus 3.
Okay, and here's the deal. It could be positive 1 times positive 3, right? Or it could be negative 1 times negative 3. Don't forget about the negative possibilities. Alright? Does that make sense? Okay. The leading coefficient is what? It's 2, right? So the factors of 2 would be 1 times 2, negative 1 times negative 2, right? So here's the deal. We have possible zeros. Okay? I like to start with the ones that come out to be integers. Okay? So, factors of the constant term. I have plus or minus 1 or plus or minus 3. And that's going to go over plus or minus 1 or plus or minus 2, right? So I could have a positive 1 over 1, right? 1 over 1 would be 1. I could have a negative 1 over 1. So that would give me negative 1, right? I could also have a positive 3 over 1. So that would give me 3. Or I could have a negative 3 over 1. So negative 3. Okay? I could also have all 4 of these possibilities in the numerator over positive 2. Okay? And really, guys, with the positive and negative, if I did all these with a minus 1, I would just get the opposite. So it's not going to really give me anything new. I can just look at 1 and 2. Do the plus or minuses on the numerator, just do all the positives on the bottom, okay? Because you're just going to get a lot of repeats if you don't. So, now if I put it over 2, I could have a positive 1 over 2 or a negative 1 over 2. I could have a positive 3 over 2 or a negative 3 over 2. Okay? Now that's a lot of possibilities. We have 8 different possibilities here. Does everyone understand how I got those possibilities? Is there anyone who's looking at that and saying, I have no idea why you have a negative 1/2 up there? Okay, we've got that part. Alright, so how do we figure out if these are actually zeros?
Plug them in.
We could just plug them in, or what's a little faster way, maybe?
You put them in synthetic division.
We could use that synthetic division part. And I would say that actually will be kind of the preferred way. Maybe not when we have a cubic, because once I find 1 and factor it out, what do I end up with? A quadratic that I could factor some other way. Okay? This is like a last resort. I don't know any other way of factoring this thing, so I'm going to use the rational zero test. Alright? If I just plug it in and I get 0, then it is a 0, and then I could always go back. But let's run through the process, okay? Or actually, let's divide up this process and see what you guys come up with. Alright, we have 18 of you, and there's 8 possibilities. Alright, so let's see. We'll start with the fractions.
2 verses to a number.
Yeah, how about if Marcos and Matthew, how about if you guys do negative 3/2, you do positive 3/2. If you two will do negative 1/2. If you two, Louise and Howard, if you guys could evaluate for 1/2, okay? If you guys could do negative 3, and then Chi-Chi and Andrew, if you could do positive 3, if you guys could do negative 1, and then positive 1, okay? We ran out, so you guys can pick whichever one you want. Double check that. Okay? So try it. Set it up with the synthetic division.
Wow, here's the first one.
What?
Nothing. This is-
I can't even see.
Set it up with the synthetic division. Try your value. Okay? And see if yours ends up being a 0.
Wait, we're doing it. No, you just plug in the, or you plug in the positive. You plug in whatever here.
Oh, gotcha.
It's not us. It's not us.
Two.
Oh, okay.
Two times
You are
negative
familiar with it. I know what H plus sign is.
0, 0, negative 6,
I know.
negative 4, negative 4. That's why I always do that.
Yeah.
Because it's the first one.
Mr. Hickson,
No,
have you
like,
graded
it's a lot of times just ones.
I have not.
Alright,
No.
I can check.
Okay, when you did negative 3 halves, what was your remainder?
15.
15?
Yes.
Yeah.
Alright, so is that.
No.
No, it doesn't work. Positive 3 halves. 9 over 2? That didn't work. We're still working on negative 1 half? That's okay if we are. You got it? Okay, so negative 1 half worked. Okay?
I did 1/2.
Oh, you did positive 1 half?
No, I did negative 1.
You did negative 1 half and it worked?
Yeah.
Did positive 1 half work for you guys?
Yeah.
Howard? You with it? Okay. Alright, how about negative 3?
Yes.
Yes? 3? No? Okay. Negative 1? Did not work? Okay. How about positive 1?
Yes.
You got 0?
Oh.
Did you get 0 for your remainder?
Oh, the positive 1.
For positive 1?
Oh. Yeah.
Yuman, did you get 0?
Calculated.
Okay, so we need to think about this, because what's the problem?
There's 4.
We got 4 zeros. How many should we get? At most, we should get 3.
I didn't get 0.
I think the
I
negative one.
Okay,
When I
Yeah, I
got-
think the negative
Guys,
is
just
4.
like-
When I got 1,
Let's try it.
Remember,
When
you
I-
plug
when
it in
I got
as the
1, it
number,
didn't
not
work.
the negative.
Alright, hang on, let's try this.
I did
Let's try this real quick. Add down, multiply, add down, multiply, add down, multiply, and we get 0. So 1 is correct.
Yeah.
I'm feeling negative
My
one.
bad.
Okay? So that's good.
Ow! You did negative.
Now,
Isn't it fairly odd to get like 1/2 and negative 1/2?
I don't know. You can. You guys want to try one of the 1/2s?
Yeah.
Yeah, wait, negative 1/2 doesn't work.
Negative 1/2 does not work. Let's try it.
There you go.
No, let's
So here, 2 times negative 1/2 is negative 1. Add down, that's 2. That's negative 1 again. Add down, we get a negative 9. Times a negative 1/2 is a positive 4.5. And you add down and you do not get 0. So
So close.
that one actually doesn't work. So there we go. There are 3 zeros. Now question, do you have to find all 3 of them using the rational zero test? No. Okay. Would I even recommend doing that? No. Okay. So once you did 1, let me go back actually to where we had that result. A little bit further. There we go. Okay. When we go back here and we have that result and we know that this is not a 0 anymore, at that point we now know that this factors into x minus 1 times the 2x squared plus 5x minus 3. Okay? And then you can take this and you can factor it further. Okay?
That's almost the exact same number as before.
It's almost, except the 3 is negative this time, so it messes things up a little bit. So I'm gonna have to do this by doing a plus 6 and a minus 1. And to get the plus 6, I'll have 2 times a positive 3, and then a minus 1 there. Okay? And notice, by the way, here's our 0 of -3, here's our 0 of positive 1/2, like you guys found as well. Okay? So, are there any questions? One thing that doing this really takes is a careful attention to detail. Okay? And also just not getting sloppy. Okay? Pick some kind of an organized way to work your way through. I usually do the integers first, because they're easy. Okay? And then I'll work to doing the fractions, because sometimes those get a little nasty. Okay? Now, as you can see here, the number of possibilities, we had 2 prime numbers, and we had 8 possibilities. So you can imagine how many possibilities you'll come up with when you've got, things with 2 or 3 or even 4 pairs of factors. Alright? This process can take a while. Alright? Check this out. Here, even with a 2 and a 6, alright? 2 only has a pair of factors, 1 and 2, it's prime. And then you have plus or minus 1, plus or minus 2. But then you have 6 that has 1 and 6 or 2 and 3. And you can see that as you go through the process, it might take a while to find one that works. Okay? One thing I will say though, do not erase your attempts. Okay? Number 1, you'll forget which ones you've already tried. And number 2, okay, it is possible that you could go through and try them all and you don't get any, and you know you're supposed to get at least one. Okay? So you must have done something wrong. So you can go back and double check to see where your mistake was. Marcos?
How does this take into account multiplicity? Like, what about?
That's a good question. Once you factored it once, it's possible that it could work again for the same number. Okay? For example, here we have this cubic. Alright? I tried a whole bunch of possibilities. And finally I got 2/3 to work. Okay? So you look at what's left over. Once I got x minus 2/3 as a factor, okay, then I knew that was 6x cubed plus 3x, 6x cubed squared plus 3. Sorry, 6x squared plus 3. And then I could see, okay, well, I can get the rest of my zeros from that. And once you get down to a quadratic, I don't care how you get it. If you want to keep using this process, you can. If you want to use a different process, you may want to. Okay? So, in this case, you get imaginary zeros, so this process wouldn't get you anymore. Anyways.
Mr. Newton?
Mm-hmm.
So do the roots represent the x value at which like the graph stops curving one way?
No. Where are our zeros on the function?
No, the roots. Like where so let's just say it had a quadratic and it
Yeah,
never touched.
I know. The roots are where we get our zeros from, right? Like this has 3 roots. 2/3 and plus or minus I radical 2/2. Okay? If you found all 3 of them, those are our 3 roots. So, those roots, any real ones, are zeros on the graph of our function. Okay? So, where is the 0 on the graph? Zeros are also known as x-intercepts. So this graph will actually cross the x-axis at where x is 2/3.
But you said, so what if all the values are imaginary? You said that the p's and q's always will give you at least one.
They will always give us at least one.
Even if there are none? Wait, I don't
Well, actually, you know what? I take that back. Any rational roots that there are, you can get with this.
Okay.
I get what you're saying. Like, it is possible to have, you know, a quadratic that goes like this. There are no real roots. Okay, so yeah, I'm sorry.
So the roots are just where the zeros are.
The roots are where the zeros are. Okay, so if you don't, if you work through all of them and none of them work, then you may have all imaginary roots, and that would be really mean of me to give you a problem like that. Huh? So, where you try 18 different possibilities and none of them work. Okay, but it's possible. Okay. So, try one here. Okay. What are the possibilities?
Whoa, hold up, okay.
That's gonna be a lot.
But here's the thing, there are a lot of possibilities, right?
Oh, yeah.
Because we have 12 and 10. But we only need to find one that works.
Was that a hint? We only need to find one.
Oh, I don't know, I don't remember the answer to this one. So,
Now when you pull on the test, but we only need to find one. Like, are you unline the word one?
no, I'm not one for subliminal messages or anything like that. So.
Good one, Tyler.
Yeah, only
Basically,
questions.
So are we not gonna have class again until
I have a
Thursday?
question.
Like an actual,
Yeah, Missy ball.
No, we don't.
we're gonna be,
Oh, whoa.
If it's all questions,
That's weird.
you're weird.
Thing.
She whiz.
oh, yes.
You got one already?
Yeah, it's the first one I tried.
Oh, good. Hey.
Finish that one.
I don't want to help us out.
It's rubber just to write all the P over Q's.
You got 4.
Fit them all in.
There we go.
Okay. So those are all our possible numerators. Plus or minus 1, 2, 3, 4, 6, or 12. And then the denominators, remember you don't have to really include the plus or minuses because you got them all on top. So 1, 2, 5, and 10. Those are all. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Then plus or minus a half, plus or minus 2 over 2, plus or minus 3 over 2, plus or minus 4 over 2. By the way, you can eliminate possibilities. What did it say about the pairs of factors that you would use? They wouldn't have a common factor. So am I going to bother trying 2 over 2 or 4 over 2 or 6 over 2 or 12 over 2? No.
Why not?
Well, because
Oh, the B.
2 over 2 is 1 and I already tried that, right? 6 over 2 is 3, I already would have tried that. Okay? So you can limit the number of possibilities you have to try for these. But it's possible that one of our roots is a negative 12 fifths. Okay? Has anyone found one yet?
I found, but I can't like factor it past x squared.
Okay,
Like, I
so
just-
you got
I got 2.
you got 2, so you tried 2. Alright, so 10, negative 15, negative 16, and 12. So here's 10, 20, 5, 10, negative 6, negative 12, 0. Okay, good. So it's x minus 2 times 10x squared plus 5x minus 6.
I can't tap everything on that though.
Because you need a difference of 5, right?
Yeah, I can't find
So
I tried one app and it worked.
I don't know. Here's the thing: if you can't find one, you could always do rational zero test again. So,
So quadratic formula.
all right,
Yeah.
or quadratic formula. True.
it.
Alrighty. Have a great day, guys.